This is Algebra 1 pre-course test. This is page 4, and we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 problems. So a couple more problems in page 4. There's just lots of multiple parts to questions. So it's a little bit more in depth today. So, all right. So number 27 says simplify x to the third to the fifth power. So when we have a power, we need to remember the law of exponents. When we have like bases, so when we have x to the second times x to the seventh, we're going to add their exponents. When we divide, when you have x to the fifth divided by x to the second, you're going to subtract the exponents. And when you have a power, in this case, we're going to multiply those. So we have x to the 3 times 5, or x to the 15. And think about it. If this is the power, and this is the base, we have 5 of these. We have 5x to the third. So x to the third times 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 x to the third. 5 of those. That's 3 plus 3 plus 3 plus 3 plus 3, or 3 times 5. So, good one. Like exponents. Evaluate 64 to the 5/6. So another interesting concept. When we have x to the 1/2, that actually equals x to the first power, and then taking the square root. So the denominator is the root, and the numerator is going to be the power. So if we saw y to the 3/2, that's going to equal y to the third and then the square root. Okay, so in this one, we can flip it. We have 64 to the 5/6, so that's going to be 64 to the fifth, and then the sixth root of it, because that's the denominator. Now, 64 is a very special number. We know that 8 times 8 is 64. And we can write 8 squared to the fifth, which would be 8 to the 2 times 5, or 8 to the 10th. And then that would be the sixth root. Now, 8 is also a special number, is a unique number. 8 can be written as 4 times 2 to the 10th. And 4 can be written as 2 times 2. So 8 is really 2 times 2 to the 10th, to the sixth root. And 2 times 2 times 2 can be written as 2 to the third to the 10th. And 2 to the third to the 10th is 2 to the 3 times 10, or 2 to the 30th. And now we can actually go backwards and write that as a fractional exponent. And 30 over 6 is 2 to the fifth. And then 2 to the fifth is equal to 2 times 2 times 2 times 2, which equals 32. How crazy is that? What a bizarre way to go about doing that. So that is a really fun, advanced, knowing your exponents on how to simplify, because we couldn't simplify it in this manner. The fraction couldn't be simplified. There weren't 6 64s to cancel that power, that exponent. Because remember, if you have the square root of y squared, a square and a square root will cancel each other. Well, nothing cancels here. We don't have that similarity We have fractions that we can simplify, but you don't have it until you get down here. And now that's where they start canceling each other. So lots of practice needed for that one. You better know your exponents. That's definitely something you need to work on. Consider the function f of x equals 4 times 6 to the x. And then you have g of x takes that parent and it's going to increase its exponent or decrease its exponent, and it's going to move its intercept. So what ends up doing, what does that exponent up on the top do? It's very interesting to see how that affects the graph. So actually, let's go back to Desmos. We were just at Desmos. And let's take that and let's put the parent equation. The parent equation is, we don't have to do f of x, but we can do f of x equals 4 times 6 to the x power. So we get this. This is called an exponential because our variable is in the exponent, and that is a increasing, and what is that called? Why can't I think of it? Growth. This is a growth formula because it's growing as you go to the left. Now let's take its parent, or let's take the manipulated one, and before we start doing multiple things, let's just do 4 times 6, and then let's see what negative 4 does. To the x. So what does the negative 4 do? Right, if we turn it on and off, what does it do? Well, what it does is, notice, it's just shifting it. And if you have 1, 2, 3, notice that intercept keeps going down, 4. So it's going to move that intercept down 4 spots. So my intercept, you saw what not on that one, with the red one. So what is my intercept? My intercept is 4 here. What value for y makes 0, right? 0, 4. And then if we do minus 4, notice it moves that intercept down to 0. Okay, so that's one thing. So we see how that affects it. And let's turn that off a second. Let's do h of x. Let's make another equals 4 times 6 to the x. And now let's do the, minus 5. Minus 5. What does that do? Oh, that kind of moves it too, right? You see how it shifts? Sorry. Yeah. Minus 5. Oh, no, stop. Why doesn't it? X minus 5. Whoa. Maybe I have to do parentheses. There you go. Well, that's interesting. Okay, so notice now what it does is it's shifting it. Notice how much it's shifting it. So let's take that point again. Let's take our intercept. And if we look at that same, notice where it is. Notice what it does. It shifts it 5 places to the right. So this moves it left and right. This moves it up and down. So if I take both of these, let's turn them off. Let's do j of x equals 4 times 6 to the, let's do parentheses because x minus 5. And now let's get back down, minus 4. So this graph, what does it do? It shifts it down and to the right. So if we needed to explain what the transformation of that graph is, it's going to go 5 units to the right. That was the exponent shift. And then it's going to go 4 units down. And that was this part. Okay, so if I gave you something like m of x equals 4 times the quantity 6 to the x plus 2 plus 1, what do you think the shift's going to be there? The shift is going to be 2 units left, because this is left and right, and 1 unit up, because this is the up and down. Cool. That was just a little practice one. Make sure you understood what was going on. Kind of neat. All right, identify the asymptote of the graph of G. So the asymptote. So let's do this. Let's go back here. Let's go back here because we're really good. Big ideas, learning, asymptote. I don't know if I spelt it correctly. Nope, asymptote. All right, let's see what big ideas, learning, asymptote definition. So, big ideas learning tells you that the asymptote are key concepts of pre-calculus, calculus. Whoa! Big ideas learning asymptotes is a line that the graph approaches as the input or output values tend towards positive or negative infinity. So, vertical asymptote, horizontal, and oblique. All right, so if we look at this graph, let's look at the purple. What are the asymptotes? Well, we know that it's moving towards a vertical, or this is vertical. It'll go to positive infinity. It has a horizontal, so this only has a horizontal. It doesn't look like it goes, but if you kept going, this would go all the way to positive infinity. So don't be fooled that this is going towards a limit. It doesn't have a limit. This is the only one that has a limit, okay? And it's never going to cross. And what is that line it's never going to cross? It's never going to cross -4. Why will we never, notice, why will it never reach negative? Oh, well, it says -4, but I think that's just an approximation. No? It says it equals -4. No, shouldn't it be? No, it does say y equals -4. So for, let's see, identify the asymptote of the graph of G. Asymptote is -4, y equals -4. Equals -4. Huh. Is it never going to equal? Is it ever going to equal -4? Oh, y equals -4. Or g of x. Sorry. I kept thinking of the x value. Sorry. Well, that's what the asymptote, I mean, it looks like it, right? So the asymptote is where it tends to head towards, so it's heading towards -4. Okay. And if we drag this way, if we drag it way over there, notice it's never going to go further than that. Okay. So those are asymptotes. It has, I guess it would, yeah, we already said it's a horizontal, so it's going to go through the y-axis. That's why my answer is y equals -4. That's good. Okay. Find the domain and range of G. So the domain. So my domain, what are my x values? X values, I can plug in any x value. So x is going to be the domain. Domain is set of all real numbers. All real numbers. There's no numbers that I can't input for the domain or x. And the range, as you saw, is going to be y is greater than or equal to -4. Oh, it can't be equal to it. Oh, that's interesting. Even though it says that it's equal to. I know, I kind of said that it wouldn't equal -4, but when we went on there, it said that it was. So I'm going to say that the range is y is greater than -4. I don't think it ever hits -4. Let's talk about why that is the case. Why can it not equal -4? So let's take this equation. G of x or y equals, we have 4, 6 times 6, x to the -5 minus 4. Why is y never going to equal 4? Why is this value never going to equal 4? Because we can get this. I'm trying to think of that reasoning behind it. I thought about it for a second. This value, yes. This value is never so this, when would this equal? Why would this not equal -4? That's adding, that would be 0. This, there you go. This will never equal 0. It could never equal 0. There's no value. This is never going to be a negative value. Or, right, what would, this is never going to be 0. Any value that you input here, because that's the only way you can get 0. Right? That's the only number. This has to equal 0 in order to 4 times something to equal 0. So this will never equal 0. If it's 0, that equals -5. If x is +5, that just makes 5 minus 5 is 0, and 6 to the 0 is equal to 1. So that would just give you 4. 4 times 1. So when x is 5, my output is going to be 4, right? Because this is 1, 6 to the 0, and that's 1, 4 times 1. So we're never going to get, and if you did negative numbers, that's just to the -6, and 6 to the -6 does not make a negative number. It just makes a small number, and that is 1 over 6 to the 6. So it just makes a super small number here times 4. So we're never going to be able to get a 0 value in there. Okay, so, and that would be, and what would get rid of it is the -4. So that's why it's my asymptote. That's really super complicated and probably not an 8th grade concept that you're going to understand at this point, especially with the limited work in exponential, especially with variables in the exponent. So that'll come as you saw, it said calculus and pre-calc. So the more work you do, and you'll see it in Algebra 2, where you're working with exponents, graphing exponential variables, you'll see how things are working a little bit better. So we'll do a little bit more work this year, but domain and range is important, but asymptotes is a little advanced. Okay, so don't worry about that at the moment. If you understood it, great. If you didn't, we'll work on it. Number 30. 30 is a 2-part question. A city has a population of 435,000. The population Y increases by 5% each year. Write an exponential function that represents the population after T years. So this is the interesting one, right? This is definitely advanced. Do we have to write a function? No. Just write an equation. Write an exponential function. Oh yeah, it says exponential function. So let's do f of x. F of x equals, and what you do is you take the original population, 435,000, and you're going to multiply it by 100% plus the 5%, or 105%. It's the original population plus the increase plus the increase each year. So that gives you 105%, which is 1.05, and then you put it to the t power, and t is representing the years. So this is a function notation, and this is kind of cool. This is how exponential growth formulas, it is growing, so we would expect it to look like this. As the years increase, the population is going to increase. Okay, and year zero would give you what for this value? 0 would give you 1. 1.05 to the 0 power is 1 times that. So on year 0, we're going to be at 435,000 at 0. And then as it grows, it'll take the original and then it'll calculate in the growth part. Real good. Hopefully now you're getting a little bit more. Another example, another something that you can sort of put in your head and see what's going on there. A city has a population. The population increases. What will the population be after 11 years? So f of 11 equals 435,000 times 1.05 to the 11th power. And we can put that in our lovely, hold on, I'm plugging in my computer too to get a little power. Okay, so we can go to Google Calculator. Google Calculator, and we're going to do 435,000. What? 435,000 times 1.05 to the 11th power. And that creates, too bad I can't copy. I can copy. That creates that number. That is the population. And to the round your answer to the nearest thousandth. Okay. So f of 11 years. So tens, hundreds, ones, tens, hundred, thousands. We're going to nearest thousands. So we look over here and we're going to get 7, 4. This tells me to round up. So the population, sorry, one more 0. Population after 11 years is this many people. And that's kind of neat, right? I mean, that should be seen as kind of cool, that you can calculate out populations knowing the growth each year. And that's how many people we would expect. So almost doubling after 11 years. Number 31, determine whether the table represents exponential growth, exponential decay, or neither. So if we graph them, we could graph them. Let's not take that. We could graph 1, 2, 3, 4. We're going up to 27. Let's go up to 27. Just make it bigger. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24, 25, 26, 27. And we go out to 7. 1, 2, 3, 4, 5, 6, 7. So 1, 6. 1, 2, 3, 4, 5, 6. 3, 13. 2, 3, 6, 7, 8, 9, 10, 11, 12, 13. 5, 20. And 7, 27. All right, so graphing it on this makeshift isn't really very accurate. Kind of looks like it's straight, but it doesn't. So let's look at the slope. Let's look and see. Well, first of all, it's growth, right? It would either be growth or it's linear. So this is plus 2, this is plus 2, this is plus 2, this is plus 7, plus 7, plus 7. So since the slope is 7 halves, and this slope is 7 halves, and this slope is 7 halves, it is neither, because this is a linear function. Okay, so that is not. We can also put it on Desmos, because you know that I love Desmos. So this is a linear growth. Okay, so not exponential. Oh, this is good. Here we go again. All right, so let's look at 36. 36 can be written as 6 times 6 to the x. And that could be written as 6 squared to the x, or 6 to the 2 times x, or 6 to the 2x. And now that equals 6 to the x minus 3. And exponent powers, if you have the same base, then the exponents, and they're equal, then the exponents. So we can actually take that and write 2x equals x minus 3. Let's minus an x. Let's solve for the variable. X equals negative 3. How cool is that? So 36 to the negative third is the same as 6 to the negative 3 minus 3, or 6 to the negative 6. Yeah, kind of cool. It's a really fun. Another one. That's more Algebra 2 work, but you will be introduced to it a little bit in Algebra 1. 33, write the next 3 terms of the geometric sequence. All right, so what is the formula for a geometric? It is not going to be increased by addition and subtraction. It's actually going to be increased by a multiplication. So let's take a look here, and let's do what we did again. Big ideas learning. Geometric sequence formula. So the geometric formula looks like this. So geometric is, let's take that. No, I don't want that. Okay. Constant, common ratio. Yeah. Let's take this. Good. Whoops. Let's take that. How do I find R? How do I find the ratio? I think it's going to be a, well, let's see, formula, finding ratio. Finding the ratio. Do you plug it in? I think you almost plug it in. It's common ratio often denoted by R, constant factor between the consecutive terms. To find, you divide any term by its preceding term. Yeah, I knew it was a sub 1. Okay, so if we do 18 divided by 9 divided by its preceding, that gives you 2. And 36 divided by 18 equals 2. So my R is going to be 2. So write the next 3 terms of the geometric sequence. So we're multiplying by 2, multiplying by 2, multiplying by 2. So we would just multiply those by 2. 72 times 2. So the fifth term is going to be 144. Sixth term is going to be 288. And seventh term is going to be 576. Now let's use this. Let's see. So we wanted the 7th term. So if I want the 7th term, I take the first term and multiply it by R, which is 2 to the n minus 1. 7 minus 1. Let's write that. 7 minus 1. Okay. So if I want the 7th term, a to the 7th equals 9 times 2 to the 6th. a to the 7th equals 9 times 2 to the 6th, which is 64, I think. And what's 64 times 9? 36, 54, 576. So a to the 7th equals 576. So very, very cool. That's showing how we can find any term, not just by multiplying it by 2, which is time consuming, but if we wanted to find the 20th term in the sequence, we could also do that using that. Cool. Very similar to arithmetic, where you have a base formula that you can utilize. All right. Write a recursive rule for each explicit rule. Okay, so what was the recursive to explicit? I think we have to find a sub 1, yes. So let's do the first. I think this is good. Let's do what is the first term in the sequence. So the first term in the sequence is going to be 2. So we would have a sub n equals 2. Oh, yeah. And then, explicit and recursive. Yeah, right. Okay. So, a sub 1, yeah. This is my first term, so yeah, hello, it was right there the first time. Because this is, a sub n equals a sub 1 times your r to the n minus 1. So my r is going to be my common ratio. It's going to be 5, and this is my first term. So yeah, I don't know. Says explicit rule, recursive rule for each explicit. So let's see what the recursive rule is. Let's look at that. Big line geometric recursive rule. Definition or form. Recursive form defines each term of a sequence based on the previous term. Simpler, it tells you how to get to the next number. Sure. Okay. A sub n equals a sub n minus 1 plus d. Okay. Oh, that's arithmetic and a geometric. Defines the previous term, geometric. So r times a recursive, geometric. Yes, we know that, right? Well, that doesn't look like it's to the power, but it is to the... Well, okay. That didn't really help me. I'd have to do a little deeper dive there. But at least I know what the first term, this is my first term, a sub 1 equals negative 2, and a sub 1 equals 5. And I know my difference is negative. Yeah, I know that. So, okay. And I know that. So, I mean, it says the recursive rule for a is going to be a sub n equals 5 a to the sub n minus 1. I don't know what that means, but that's the n minus 1 term. So prior, all right, I don't know. But yeah, we use that. So it's going to be a sub n equals negative 0.2 a to the n minus 1. And this is going to be a sub n equals 2 to the a, so 2 times the term before it. Okay. Okay. Got it. Okay, meaning if you take the term before, multiply it by 2, you'll get that term. So the term you're looking for is equaling 2 times the term before it. Got it. If we want to find 18, we're going to multiply 2 times the term before it. Okay, so that recursive for that would be a sub n equals 2 times the term before it. That's that a sub n minus 1. That's the term number. Sorry. Took a little brushing up. I got it now. We're good. So to get a term, you take the term before and multiply it by 2. Kind of silly, but all right. Learn something new. Good luck.